Is another proof by induction. It's quite tricky. It involves binomial coefficients, and we're going to have to start with a little bit on Pascal's triangle because we're going to have to use an important relation to actually prove the thing. So the question is, using mathematical induction, show that for all non-negative integers n, nc0 plus nc1 plus nc2 plus ... plus ncn minus 1 plus ncn equals 2 to the n. So it's amazing simplification if you think about it. Right, so I'm going to have to use something in it. So what I'm going to do, I'm just going to take you to Pascal's triangle and show something. It won't be a formal proof, but it could be proved. So 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, so on, and 1, 5, 10. 10, 5, and 1. So if I just stop there, just think how Pascal's triangle works. You've got all these areas where this plus this equals that. So if we just take any little triangle where that's true, so if we just draw around those and just think what they are. So this, for this row where we have 4 is the second number, n is 4. So this is 4c0, 4c1, 4c2 is 6, 4c3 is 4. So that's telling me 4c2 plus 4c3, so 4c0, 1, 2, 4c3, 4c2 plus 4c3, well that equals the 10, and the 10, well n is 5 for the 10, equals 5c0, 1, 2, 3 equals 5c3. So that is just one instance of some general thing that you could have found all over the triangle. So if you think about what that means, well, it could mean that, say, n, if we've got an n on the top, this 4 could be the n, and 5 could be, in that case, if 4 was n, and 5 would be n plus 1. And then, if we think about the bottom bit, well, this is the same number. So this we could either call r and r minus 1, or I suppose we could call it r and r plus 1. But I'm going to write n plus 1c r, and then this must be 1 less, r minus 1. So this is a relation that we can use. I could put that in terms of k. So what I mean by that, I could say, well, kc r minus 1 plus kcr equals k plus 1 cr. And this, remember, the only way I got to this was just by looking at the triangle, and we could have gone anywhere for that. It's just, that's how Pascal's triangle works. And just remember what the numbers actually represent. This number is 5c0, 5c1, this is 3c0, 3c1, and so on. So this relation here, I'm going to use it in the proof. So I hope you understand where it came from. So now we say what we're going to prove. So we need to, in fact, I'll do it on the next bit. Right, so here's what we are trying to prove. The proposition Pn that we're trying to prove is as follows. So it is that for all non-negative integer n, so for all integer n, where n is greater than or equal to 0, nc0 plus nc1 plus nc2 plus ... all the way up to, well, the last term is ncn, so the second last term must be ncn minus 1. So the proposition we're trying to prove is that all of that equals 2 to the power of n for all non-negative integer n. So how are we going to do it? By the principle of mathematical induction. So proof by the principle of mathematical induction. So we will do the basis step on here, and then we will move on to the rest. So the basis step, remember it says n needs to be a non-negative integer, so a basis step can be when n equals 0. So step 1, if n equals 0, so we just have nc0, nc0. Now remember, in this triangle, it's always 1, 1, so this is always nc0 on the edge, the left edge there. So nc0 equals 1, and 2 to the 0 also equals 1. That means that P0 is true. Okay, hopefully you are familiar with these now, and you know that the next step is to assume that the kth case is true. So step 2, if pk is true, and we're going to need a lot of space across here. So if pk is true, so kc0 plus kc1 plus kc2 plus dot 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 plus kc k minus 1 plus k c k equals 2 to the k. Okay, so that is pk. I might just think about that. So in terms of the triangle, remember 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. So don't forget that the first term and the last term, so kc0 and kck are both 1. I think that's important because, well, because I know what comes next, to put it mildly. So 1 plus kc1 plus kc2 plus dot 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 plus kc k minus 1 plus another 1 equals 2 to the k. So it's not necessarily important for formalizing and presenting the proof, but it's certainly important for me to show you. So we also need to know what our target is. Target for pk plus 1 is, well, it's going to be 2 to the k plus 1, which remember is 2 times 2 to the k. We see this a lot, right? So now we're going to write an expression for pk plus 1. pk plus 1, so that equals, well, it's going to be k plus 1c0, k plus 1c0 plus k plus 1c1 plus k plus 1c2 plus k plus 1c3 plus dot dot dot, and then we're going all the way up to k plus 1 ck plus k plus 1 ck plus 1. Right, so now what I'm going to do is bring in what I was showing you earlier, because I think it's going to be quite useful. Remember, recall from the stuff with Pascal's triangle that kcr minus 1 plus kcr is exactly the same, equivalent to k plus 1cr, right? So what I mean by that is I want to kind of write these, I want to get rid of all these k plus 1s, or nearly all of them, and turn them into just k's at the top, because that's what we're going to look for, because we're going to have to find something that we can substitute a lot of stuff that looks like that. We can turn it into 2 to the power k. So we're not going to be able to do that if we've got k plus 1s at the top. So I can't do a lot with this first one, but remember I can call it 1. So k plus 1 c0, but anything c0 is just 1. So that's just 1 plus. Now this one here, k plus 1 c1, I can use that. So k plus 1 c1 is going to be kc1 and kc0. So it's kc0 plus kc1. Okay, so now if we do something similar to this, plus, and then here we're going to have k plus 1 c2. So k plus 1 c2 is going to be kc2 and kc1. So plus kc1 plus kc2. Now if you think about a pattern that's going on, I'm going to do exactly the same thing for this. You should be able to just look at these and say, well, that's going to be kc2 and kc3. If not, just look at this. K plus 1 c3 is going to be a kc3 and a kc2. So kc2 plus kc3, right? Plus dot dot dot. Now we're into the business end, where we've now got to deliver this. So what is this thing going to become? Well, this k plus 1 ck is going to become, well, it's going to turn into a kck and a kck minus 1. So plus kck minus 1 plus kck, like that. And this last term, I actually think it's more beneficial just to leave it like that, because don't forget this is the last term, and as I pointed out here and I pointed out in the Pascal's triangle, this is just 1, so I'm going to leave it like that, plus 1, right? If you now look at all of this, what I'm going to do to show you that it works, I'm going to look at this one and this one on the end, and I'm going to substitute them for this one and this one from the pk expression, because if it's just 1, it doesn't matter. So 1 has been written as k plus 1 c0 here, but it's also been written as kc0 here, so I'm just going to write it as kc0 again, equals kc0. And then I'm going to look at this one on this end. It's kc1, so it's k plus 1 ck plus 1 here, but it's also kck, so it doesn't matter. If I write it as kck, I can see the benefits there, kck, right? Now in the middle, everything else is the same. Plus kc0 plus kc1 plus another kc1 plus kc2 plus kc2, and then you're going to have 2 kc3s and so on, plus dot dot dot, plus, and if you're not sure about this, you would have had another kck minus 1, because if you just think of the term before that, the way this was going, there would have been 2 of these, so plus kck minus 1 plus another kck minus 1, and I can hopefully squeeze this kck in there. Now hopefully you can see that we have 2 of everything, so I can say 2 times kc0 plus kc1 plus kc2 plus dot 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 all the way up to kck. So now that is quite good, isn't it? Because this is 2 times 2 to the k. So all of this, remember, is our pk. So this is 2 to the k. So now we have the whole thing equals 2 times 2 to the k, which we know is 2 to the k plus 1. We've done it, we've gotten to the target, we just need to wrap it up and finish the proof. So since P0 is true, and pk plus 1 is true whenever pk is true, so since those things are the case, Pn is true for all non-negative integer n, and that is because of the principle of mathematical induction. Right, so that is quite a tricky one, but it kind of took two topics out because that relation with bits in Pascal's triangle is something that you could potentially need to use elsewhere. The basic bits were the same, and yes, even if you couldn't do the whole thing, you should be able to pick up some marks just by setting the thing up, getting your base or case, assuming that pk is true, trying to form an expression for the thing. You can still get half marks, even if from there all your algebra goes wrong.